We've engineered a spring-powered, self-propelled machine capable of generating unlimited electrical energy. Want to see how we built it? Stay until the end of the video, and you will discover all the secrets. V8 spring engine, crankshaft component fabrication. We begin by cutting a steel bar with a diameter of 25 millimeters by 540 millimeters. The ends of this bar need to be machined on a lathe. Both ends have a metric 8-threaded hole. Next, we'll mill a 6 millimeter wide keyway using a milling machine. Here we have 8 steel bushings, each with a diameter of 35 millimeters by 25 millimeters and a bore of 25 millimeters in diameter. We'll machine a flat surface onto these bushings. Now we drill a hole at each end of the component. Thread both holes to metric 6. These holes will be used to insert a metric 6 threaded stud. Here we have 8 steel pieces measuring 25 by 25 by 8 millimeters. We'll drill a 6 millimeter hole in each piece. We also cut 4 pieces with a diameter of 25 millimeters by 75 millimeters. Additionally, we machine a flat surface on each end. Then, we drill a 6 millimeter diameter hole at each end. We'll also counterbore this hole to recess the screw head. We've cut these 8 pieces to 25 by 45 by 5 millimeters. We drill a 6 millimeter hole at one end and mill down that end so it mates perfectly with the bearing surface. Now we insert this bearing into a jig and secure these components with screws. This ensures they're perfectly aligned and centered on the bearing. We weld the components to the bearing. We lubricate it with oil until it spins smoothly. And that's how we produce 4 identical assemblies. V8 spring engine, frame fabrication. We'll construct the frame using 40 by 40 millimeter square steel tubing. It needs to be a highly robust structure. We weld the profiles together. We cut 4 plates to mount the legs. In each plate, we will make a threaded hole of metric 8. We continue welding additional frame components. We also fabricate 2 pieces to support the bearings. We will machine a metric 12 threaded hole at each end. We weld a component to each end, ensuring they're perfectly centered and aligned. We'll also weld this custom-made piece, which will secure our 1 kilowatt dynamo. The welding process demands a skilled welder to prevent frame distortion. It's critical that the frame is well constructed to avoid crankshaft misalignment and excessive vibration. V8 spring engine, crankshaft assembly. Here are all the crankshaft components. We start by inserting a spacer ring to center the bearing. We slide this shaft into the bearing and add the second spacer ring. We insert in each of these pieces a threaded stud of metric 6. We'll fix the shaft and bearing to this assembly. For this purpose, we will use a 6 by 35 millimeter metric bolt. This is how each of these components should look. In total, we'll have 4 identical units. Now we'll assemble all the elements onto the shaft. We will start by inserting the shaft into a UCP 205 bearing. Install this key onto the shaft. Position these 4 components on the shaft. And finally attach the second UCP 205 bearing. We secure the bearings to the machine's frame. Now we need to precisely distribute and align each of these components on the shaft. We'll use these threaded studs to fix each piece at a 90-degree angle relative to the previous one. The alignment process must be meticulous. Otherwise, the crankshaft will be unbalanced and vibrate excessively. We proceed by welding all these components to the shaft. Now we need to cut the shaft in this manner so the bearing can rotate freely. We repeat this process for each bearing. Our crankshaft is now complete. Next, we'll fabricate the spring tensioners. We cut 8 pieces to 25 by 45 by 5 millimeters. We drill a 4 millimeter hole in each piece and cut it accordingly. We also cut 8 30 by 30 by 4 millimeter angle sections. Then we weld these 2 pieces together like this. In total, we'll make 8 identical units. We'll position them centered and aligned on the frame, 4 pieces per side. We're going to disassemble the machine for painting. We apply an initial primer coat. Followed by 2 coats of metallic red paint. Once the paint dries, we attach the 4 rubber feet and reassemble the crankshaft. We install the key and couple this 30-kilogram flywheel. We add a screw to each end of the crankshaft. Here are the 8 springs that will power our machine. We proceed by installing each spring in this manner. It takes considerable force to tension them. Once all 8 springs are in place, the machine will be ready for its first test. V8 spring engine, performance test. Let's explain how this machine works. When you give the flywheel, coupled to the crankshaft, an initial push, it starts rotating. As the shaft turns, the crankshaft's eccentricities induce linear reciprocating motion in the springs, creating successive cycles of elastic loading and unloading. This generates a forced harmonic oscillation in each spring, storing potential energy during the compression-extension phase, which is then transferred back to the shaft as rotational kinetic energy, thanks to the spring's rapid, synchronized return to equilibrium. The system operates at an oscillation frequency close to the spring's natural frequency, resulting in an energy amplification effect through resonance, minimizing mechanical losses, and maximizing dynamic coupling efficiency. The system's elasticity, combined with the frame's rigidity, ensures a significant portion of the energy stored in the springs is retransmitted to the shaft, reducing the need for external energy input once the cycle begins. If we detension 2 springs, we disrupt the compression-charge extension balance, stopping the rotational motion. Comment if you can think of a more effective way to break it. The comment with the most likes will be developed in another video. Give it a like if you enjoy this machine. Electrical power generation test. To complete our machine, we'll couple this 1 kilowatt dynamo. Using these components, we'll transmit the flywheel's motion to the dynamo, producing electric current through these cables. We mount the dynamo to the frame, install the pulley, and secure it by tightening these bolts. Now, using this drive belt, we connect the flywheel to the pulley. We adjust the belt tension by lowering the dynamo's height. The machine is finished. For the test, we'll use this panel with 8 60-watt bulbs. Connecting them to the dynamo via an electrical strip. This way, we'll harness the generated electrical energy to light these bulbs. Everything's ready. The flywheel's inertia maintains angular momentum despite the magnetic drag from the dynamo. The design synchronizes the elastic release phase with each connecting rod's top dead center, delivering an extra push precisely when the torque on the shaft is minimal, naturally offsetting frictional energy losses. At peak speed, the motion remains steady, and the generated electricity powers this 480-watt panel. Let's measure the dynamo's output voltage. We're getting 195 volts of direct current. The voltage holds steady. This prototype isn't as efficient or capable of generating as much electrical power as our previous Liberty engine prototypes. But we've proven it works perfectly. We'll include links to our various prototypes in the video description. The machine hasn't lost speed at any point. The springs continue transferring energy to the crankshaft with minimal vibration. But the moment we detension two springs, the system halts. Thanks to our members for their support. Become a member to support our videos. Subscribe and join the energy revolution.